This project is all about providing the inspiration to our visitors that they need to achieve the next great milestones in aviation and space. Through this 7-year renovation, every one of our galleries will be updated or brand new. The new National Air and Space Museum will tell the transformative stories of aviation and space in new ways to new audiences, allowing us to reach further than ever before. And don't worry, we're going to stay open during the whole project. So you will still be able to visit and attend our events, even if you see lots of cranes and fencing outside. We'll be here to continue to share the stories of aviation and space, like our speaker will be talking about tonight. Our renovation is just one of the big projects underway at Air and Space this year. Another is our celebration of the upcoming 50th anniversary of the Apollo moon landing. Tonight's event is part of that ongoing Apollo 50 celebration. This year's Exploring Space series is focusing on the moon with a look at lunar science and exploration throughout the years, but also into the future. Tonight's program is made possible by the generous support of our sponsors, Aerojet, Rocketdyne, and the United Launch Alliance, companies that have been instrumental in launching, propelling, and landing many spacecraft that have explored our solar system. Representatives of these organizations are here in the audience tonight, and please join me in thanking them for their generosity in supporting this great evening. We are extremely delighted to have Dr. Noah Petro with us here tonight. Dr. Petro earned his PhD from my alma mater, Brown University, and is currently a research space scientist at NASA's Goddard Space Flight Center. His research focuses on impact cratering and the evolution of the lunar crust. He served on the team for the Moon Mineralogy Mapper instrument that flew on the Indian Chandrayaan-1 lunar mission, and he is currently the project scientist for the Lunar Reconnaissance Orbiter that is actively exploring the moon today. Tonight, Dr. Petro will speak to us about looking at the Apollo landing sites and the broader moon with new eyes. And it's now my pleasure to introduce Dr. Noah Petro.
Thank you so much. Okay. Well, first of all, I want to thank everyone for taking time out on a Wednesday night, a beautiful Wednesday night, to come in and listen to me wax poetic, or try to wax poetic, about the moon. Just having watched that video, it reminds me that I spent a lot of my time as a kid in this museum. My father lived in Arlington, and we would come here as often as I could. I spent more time than I care to remember in the Apollo exhibit, poring over every artifact, wondering why the scissors were shaped kind of funny, and why were the things that were on display there, and why is it that you had this giant rocket, but only that very tall top portion was on display here. And my father, being very patient, explained all of it to me, and we'd come back, and we'd come back. And now living in the area with 3 small kids and being able to take them here, taking my son when Discovery was put on display, really the first weekend it was brought in to the annex out by Dulles, and to pass on that interest in not just space, but in learning about our history of flying, of space exploration. My daughter Amelia, you saw the Amelia Earhart exhibit on the video. It's hard not to feel like coming to talk here tonight is some sort of cosmic retribution for having put my father through all of that, and having put my kids through all that now too. But it's really so deeply moving for me to be here tonight, and I can't thank you enough for everyone for coming out to hear me speak. This is a really incredible time to talk about the moon, to be thinking about the moon. And as much as I, several months ago submitted a title for this, I really think the title for this should have been Why the Moon? Why the moon 50 years ago, and why the moon today? And I don't know that I'll get right to the answer eventually, but I hope that I'll win my way there. And maybe that's the question someone should ask at the end. But let's start with where we are today. This is a visualization of what the moon should look like if it's clear tonight, based on data from the LRO spacecraft, the Lunar Reconnaissance Orbiter. We take the topography data that we've gathered for the moon, we take the color of the moon that we've gathered from our camera, and we can reconstruct what the moon looks like basically at any time in history. Whether you want to know what the moon looks like tonight, or hundreds of years ago when Galileo first trained his telescope on the moon, we can understand what the moon looks like. And so tonight, if it's clear, when you go out, I want everyone to look out at the moon and think about what do you see? What do you see when you look at the moon? Do you see, as some astronomers do, just see a bright source of noise in their data? Or do you see something more poetic, more inspirational, or, in my eyes, something geologic? Some connection to space, to the history of the solar system recorded in the surface of our next door neighbor. And as I said in the introductory portion, I see another continent of the Earth waiting to be explored, again, 50 years after we started that in situ exploration. And so hopefully everyone has an opportunity to go out and look at the moon. I always encourage folks to go out and look at the moon, whether it's full or not, whether it's a supermoon or not, to go out and look at the moon and just appreciate that we, unlike any other object in the solar system, have something as spectacular as our moon as a neighbor in space. But before we look up, let's look down for a moment. This is a picture taken, incidentally, one day before my son's 8th birthday last year by the Expedition 55 crew on the International Space Station. Now, your orientation's all wonky. I chose not to reorient the image. But of course, you can pick out some of your favorite landmarks. Here's the Capitol. We are right in here. National Airport. The bridge that I spent far too long crossing tonight coming into town. And I wanted to include this, one, as a reminder that we have astronauts in space right now, taking beautiful pictures of the Earth, but also to get everyone thinking about where we are right now, Washington, D.C. And if you had a visitor, two friends coming from, let's say, Australia, to visit us here in D.C., but they could only go to 6 places in Washington, where would you have them go? Don't all shout out at once. Now, hopefully, you've got, it's funny, when I talked to a colleague at work, the first place that we both mentioned was going to Ben's Chili Bowl. I think that's more reflective of our hunger and appetite than anything else. But what if they only went to, and this is not a slight against these museums, what if they only went to, of course, the Air and Space Museum, but what if they only went to the Air and Space, American history, natural history, American Art Gallery, maybe the Botanical Garden? What if they only stayed on the mall? Would you say that they got the full DC experience? They got a DC experience, but not the full DC experience. I want you to keep that in mind as we talk about the Apollo exploration of the moon. Okay. As a reminder, we're not only celebrating the 50th anniversary of the Apollo missions, but the greatest precursor set of missions a robotic orbiter could ever ask for, the 10th anniversary of the Lunar Reconnaissance Orbiter. As was mentioned, I'm the project scientist of LRO. That means I get to take the 7 science teams, the instruments that we have on our spacecraft, and get them working as one. It's a great experience. I've learned more about not just lunar science, but about science and management and personalities, and getting these 7 incredible teams working together towards a common goal. So as we celebrate the 50th anniversary of Apollo, the 10th anniversary of LRO, it's important to remember why we care about the moon and take this forward so that when we celebrate the 60th, and well, maybe we'll get to the 20th anniversary of LRO, I don't know. As a robotic explorer, every morning I check my email, half expecting to get something happened last night. But fortunately for 10 years, again, a mission that was really planned to last 1 to 2 years, we are doing incredible things. We've created a volume of data larger than any other planetary science mission in the history of NASA. Of course, we benefit from being very close to the Earth, but we also benefit from having incredible instruments that are completely revising our understanding of the moon and essentially leading to a rewriting of the textbooks of lunar geology. This is an example of some of the kinds of data that we're collecting at the moon. On house right, we have a wide-angle camera, a mosaic of what the near side of the moon looks like, revealing the dark volcanic lava flows that cover portions of the lunar near side, as well as the brighter North Acidic highlands crust, the ancient crust of the moon, heavily impacted over 4.5 billion years of cratering. On the other side, we have a topographic map the highest resolution topographic map we have of any object in the solar system, including the Earth, comes from the moon. This is thanks to a laser altimeter flown by a group based out of Goddard, so there's a lot of institutional pride there. But this data that we have now reveals not just the character of the moon, but also paves the way forward for understanding where we want to go when we do inevitably return. We also have another instrument that's quite remarkable. It's called Diviner. It's a radiometer, which is a fancy way of saying it's a thermal instrument. It's measuring the radiation, the thermal radiation coming off of the surface of the moon. What you're seeing here is a map of what we call rock abundance. If you've ever been to a beach on a hot, sunny day, the sand gets very, very hot in the middle of the day and cools very quickly at night. Whereas large rocks, boulders that are the part of the retaining wall at that beach, they absorb heat much more slowly. They warm up, but they also cool down much more slowly. So we have this radiometer that is measuring those temperature variations on the lunar surface. We can use that data to understand the properties of the surface. Where are there, it's not quite sand, but where's this fine powdery surface? Where are there larger rocks? And so this is a map basically of the density of large rocks. And not surprisingly, the areas that are most enhanced in rocks are surrounding younger impact craters. This is the famous Tycho impact crater on the near side. We've got Aristarchus and Copernicus, and then lots of very, very small impact craters that excavate boulders. As a geologist, these boulders become very interesting. The engineers say that staying away from boulders is very interesting, and therein lies the dynamic of wanting to go to these areas that are, of course, enriched in boulders. And as I'll show, actually, these areas that are enhanced in boulders are not that dangerous. They actually are quite interesting areas and awesome locations for future potential exploration. So this is the moon as it was not tonight, but almost 50 years ago, on July 20th, 1969. I was still about T-minus 10 years from launch at that point. Not quite, but almost. And looking across the audience, I don't know that anybody in the audience was around for Apollo 11. So let me set that back. Always try to get on the audience's good side. But if you looked up on the moon, at the moon on July 20th, 1969, this is close to what you would have seen. This is similar to any moon that has come around since then, but this, of course, was a very important date in not just NASA's history, not just American history, but, of course, in the history of the world. We're about to embark on one of the most incredible, not just adventures, not just engineering exercises, but one of the most incredible scientific endeavors that we've ever set out. But, of course, science wasn't part of it. Science was never the goal. And I can try to talk all I want about what Apollo is about, but I think I'd rather rely on the words of really the one person who inspired it and made this possible, which is not this slide. And that is the danger, kids, and changing slides early on. But what I do want to emphasize is the idea that when we go to the moon, whether it's with humans or on the right, picture of our Earth taken from our camera on LRO, or indeed when we're in Earth orbit from the International Space Station, we get views of the moon from Earth and, of course, the Earth from the moon. And what this reinforces is that we share the same space. Thinking of the moon as something foreign and unusual to the Earth is really not, I think, scientifically or even emotionally appropriate. The moon is a neighbor in space, and just like my neighbors reflect kind of what goes on in my neighborhood, they like it when the newspaper's delivered on time and the trash picked up on time. The moon reflects the things that are happening in our neighborhood. But of course, when we started the goal of going to the moon in the 1960s, the idea of understanding our neighborhood was really far removed from our cognizance, our understanding of what we would learn. And I think it's important to remember that everything that we've learned about the moon comes because we set out the goal of wanting to go there. And so now, if I followed my outline properly, we'll hear why, at least at the time, we thought we would go to the moon. And this was to beat the Russians. That's it. Beat the Russians. So I've never been good at math, 58 years ago, as we speak, there was this great tumult going on. In April of 1961, Yuri Gagarin blasts off and orbits the Earth. This sets in motion this, I think it's fair to say now, this scramble to figure out what could we do to top that, to beat that, to overcome what Russia had done. And as I turn, a week later, basically, the president asks the vice president, what can we do to beat the Russians? What can we do to beat them? A week after that, and trust me, working in the government right now, things turned around in a week is remarkable. LBJ responds by saying, well, we can go to the moon as an achievement. We can be first on it, and we might even be able to do that by 1966 or 1967. And let's also remember, and this is something that I learned recently from my father, who was an engineer on Apollo, that 1967 date was very important. November 1967 would have been the 50th anniversary of the Russian Revolution. And so I think there was a real thought that they were going to try to pull something off in November of 1967. And so that probably early on became a real important goal. Let's try to do something by that point. A day later, Wernher von Braun, who incidentally is buried in Alexandria, Virginia. I took my kids to see his grave. Perhaps not the smartest move a parent has ever made. But again, as a point to explain who this person was and why the boot prints we have on the moon go back to this gentleman. And there's an underlined line right here from his memo, April 29, 1961. I think we have and I'm paraphrasing here, we have a chance of beating the Soviets to be the first to land on the moon. And later in that paragraph, he says they may actually be able to fly one astronaut around the moon before us, but I think we could land before that. And in very short order, and we're coming up on the anniversary of this speech, of course, Alan Shepard makes his first U.S. flight into space, and 20 days later, JFK delivers his famous speech. I believe that this nation should commit itself of achieving the goal of landing a man on the moon and returning him safely to the Earth. I think that's also, let's just compare to what's happened recently, the verbiage that's being used to describe sending the first woman and the next man to the moon. And I'm so thrilled to be part of that endeavor right now. So within the span of essentially 1 month, we go from what can we do to that's what we're going to do. We're going to go to the moon. Again, the why is not a part of it. We're going to beat the Russians.
But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too. The growth of our science and education will be enriched by new knowledge of our universe and environment, by new techniques of learning and mapping and observation, by new tools and computers for industry, medicine, and the home as well as the school. Technical institutions such as Rice will reap the harvest of these gains. And finally, the space effort itself, while still in its infancy, has already created a great number of new companies and tens and thousands of new jobs. Space and related industries are generating new demands in investment and skilled personnel, and this city and this state and this region will share greatly in this growth. What was once the furthest outpost on the old frontier of the West will be the furthest outpost on the new frontier of science and space. Houston, your city of Houston, with its manned spacecraft center, will become the heart of a large scientific and engineering community. During the next 5 years, the National Aeronautic and Space Administration expects to double the number of scientists and engineers in this area, to increase its outlays for salaries and expenses to $60 million a year, to invest some $200 million in plant and laboratory facilities, and to direct or contract for new space efforts over $1 billion from this center in this city. To be sure, all this costs us all a good deal of money. This year's space budget is 3 times what it was in January 1961, and it is greater than the space budget of the previous 8 years combined. That budget now stands at $5.4 billion a year, a staggering sum, though somewhat less than we pay for cigarettes and cigars every year. Space expenditures will soon rise some more, from 40 cents per person per week to more than 50 cents a week for every man, woman, and child in the United States. For we have given this program a high national priority, even though I realize that this is, in some measure, an act of faith and vision, for we do not now know what benefits await us.
And it's that last phrase, which is why I let that video run on perhaps longer than I should have. But he ends with this line, we don't know what we'll find. That we'll go, we'll do this, and then we'll discover. He spends most of that clip talking about all the investment in companies, investments into technology, into scientists, and then in that end he says, hey, we'll also learn something along the way. And I think that sort of encapsulates what Apollo was about. We're going to do something, we're going to do a tremendous national effort, and at the end, we'll get something out of it. He didn't know that we'd learn about the ancient history of the solar system, or that we'd learn about how planets form and evolve. He didn't. But he knew that it would accomplish some great things. And so, if there's maybe one thing about Apollo that you take away, is that all of the science that we got out of Apollo was put into it after this. That the opportunity was recognized that we could learn something important about the moon, and so we better take that opportunity. And so, going back to what we talked about before the lecture, we have to take every opportunity we go to the moon, whether it's a small commercial lander or a huge national initiative, and get as much science out of it as possible. Because every time we go to the moon, we have an opportunity to learn something that will profoundly change our view of the Earth and the solar system. In preparation for Apollo, it was recognized that we better do this safely. In those notes from Wernher von Braun to LBJ, he talks about, oh yeah, we want to get the astronauts back. This is not a one-way trip. We want to do this safely. And so there were a set of guidelines, of objectives set out of how to find those safe landing sites. And really here what I want to talk about is how Tranquility Base became Tranquility Base. Nobody set out in any memo that I've seen saying this first landing site is going to become a national treasure, a global treasure. We better pick the right spot. No. We better find the safest place to go. And ultimately, the story of how Apollo 11's Tranquility Base became Tranquility Base comes down to, as most things in government do, saving money. So initially, and there's actually more objectives and requirements for these landing sites, but the bottom line is that it had to be smooth. It had to find a place that had relatively few craters and boulders. That makes sense. You don't want to land on top of a boulder or in a crater. You had to be able to approach the landing site and not have a huge mountain in your way. You also had to be on a trajectory, as anyone who's seen the Apollo 13 movie remembers, you had to be on this free return trajectory. And early on there was a concern that if something happened to the spacecraft on the way to the moon, they could go around the moon and come back without having to make any mid-course corrections. They also wanted to land on a very flat slope. And so those criteria established essentially 5 early landing sites. On this map, they're labeled P2, IP6, I don't know what the numbers stand for, but basically there were these initial set of landing sites all around the equator and all on the near side of the moon. And it was the goal of first Apollo 8 to find out what they could learn from orbit about this particular landing site 1. Now, of course, there had been the Ranger series of missions sent to impact the moon. There had been the lunar orbiting missions, Lunar Orbiter, to map the moon. And so each of these landing sites had been imaged in some way by Lunar Orbiter and some by Ranger. And so this was the first pass at what would become our initial set of landing sites. This is a set of images from the Ranger spacecraft. Again, this is a mid-1960s effort to become capable of actually going not just to the moon, but hitting the moon, which, you know, obviously eventually we'd want to slow down at the back end of this, but initially it was just a goal of hitting the moon, communicating to a spacecraft in deep space and demonstrating that we could do that. And so the green circle on many of these images here highlights what would become the Apollo 11 landing site. And so it was these first images of the lunar surface at relatively high resolution that first of all showed that there would be something to do when we got there. There'd be geology to explore, there'd be smaller craters, that the moon's surface was covered in impact craters at almost every scale, but indeed that there would be safe landing sites. Subsequent to that was the Lunar Orbiter series of missions. And of course, there's an incredible story to be told about Lunar Orbiter. And for, again, I know most of you were born after 1969, but there was this thing called film. And the film was developed on Lunar Orbiter and then transmitted back to Earth, which is why we have all of these lines, these hash marks, and some of these. If you've ever had a Kodak automatic Polaroid, you'll remember what this kind of propagated through on images. But again, the circle represents where the Apollo landing site was. Now, they didn't target that landing site. There was an ellipse, a circular, or actually an oval-shaped area that they felt that they could land safely in. And so all of these images, all of these data suggested, yeah, this landing site 2, which I showed in the map a few moments ago, met those criteria and would be a good place to land. Now, this is more of a nadir view, looking straight down and circled right in here. This is one of the final images of the Lunar Orbiter series that showed the landing site. And indeed, if you were to take an image, you know, a few years later, you would have actually been able to see a little bit of a dot right there where Apollo 11 set down. Now we go back to 50 years ago, and I apologize, the image at the right is washed out. I had not appreciated how powerful the projectors here at the Air and Space Museum are. A little bit better than the ones we have at Goddard, but so I'll have to talk to folks in capital spending at Goddard about that. But nonetheless, the Apollo 10 mission, which launched 50 years ago this week, you know, they were exploring the moon 50 years ago from orbit in the dress rehearsal for the moon. This is an image on the left of the Apollo 10 crew. Commander Tom Stafford, John Young, Gene Cernan. John Young, of course, and Gene Cernan later went on to walk on the moon. This is Jack Schmitt, who was at the time serving not only as a scientist astronaut, but in the support and planning support for orbital observations. I think at the time, no one would have imagined or even wagered that Gene Cernan would later go walk on the moon on Apollo 17, and Jack Schmitt would be his lunar module pilot. But at this point, they're preparing for what to observe from orbit. And one of the goals of their orbital observations was to indeed image the Apollo, what would become the Apollo 11 landing site. And so they did, on one approach from the lunar module, essentially practice the approach to what would become the Apollo 11 landing site, again, marked in green here. And that became the verification that NASA needed. Now, why did Apollo 10 image this second landing site? Apollo 8 had gone to the moon in December of 1968 and imaged that first landing site. If you'll remember, it was at the far east side of the moon. And so they, in addition to just showing that they could get to the moon, did take a number of orbital observations, including images of that first landing site. One of the little-known after effects of Apollo 8 was that when they splashed down in the Pacific, they splashed down at pre-dawn. They re-entered the Earth's atmosphere and landed in the Pacific Ocean in darkness. Now, Apollo 10 initially was planned to essentially repeat what Apollo 8 had done, which would, of course, then led to a nighttime splashdown. But Jack Schmitt, who I showed earlier, realized that if they had slipped the launch day by one day, they would be able to image that second landing site and have a daytime re-entry into the Pacific Ocean. Now, you might think today, well, that seems logical. Why not do that? Well, at the time, to do the trajectory analysis, to do the calculation of the orbit, was not just computationally expensive, had also then translated into a financial expense, which no one was really willing to go into this idea of, well, you know, Apollo 8 worked, why do anything different? And so unbeknownst to anyone, Jack had the folks at the time, the Manned Space Flight Center, now JSC, do that trajectory analysis. And so he went and proposed this, this launch slip of 1 day to the Apollo 10 crew and proposed it to NASA headquarters and said, well, if we do that by 1 day, you'll get a new landing site. Well, new landing site, we don't really want that. Well, you'll get more coverage. More coverage. You'll get a daytime splashdown in the Pacific. That's it. And that's what got NASA headquarters interested. And so they said, fine, go with that. And so when Apollo 10 went and scouted out this second landing site and showed that it met all those criteria, showed that it was successful and would meet the objectives, they said, fine. Apollo 11 will redo everything Apollo 10 did, land at that landing site, and get a daytime splashdown. We're good. And so it was, because a little extra money was spent to prove that Apollo 10 could do it and splash down at daytime, this became the objective for Apollo 11. And again, remember, so right now we're at the end of May, and July is coming up very quickly. And for those of us planning 50th anniversary events, far too quickly. But that was it. That set in stone the notion that this area would be the Apollo 11 landing site. And of course, on July 20th, this was an image that no one else would have seen until after the mission. But this was the first view out of the lunar module window of what became Tranquility Base. And what we see here is, as was described by the crew, magnificent desolation, a view like the high deserts of the US Southwest. We see a beautiful mixture of the pulverized lunar surface, the regolith at the surface. We see large boulders. We see what ultimately is a geologist's paradise. There's not a tree to be seen. It's wonderful. And on that first mission to the moon, of course, science was a secondary priority. The initial goal, and as of late 1968, it was going to be one astronaut getting out, collecting a little bit of sample, planting the flag, saying a few words, and then getting out of town. And it took effort. It took a lot of work to convince NASA, let's get 2 astronauts out. Let's spend more time out of there. One thing I'd ask everyone to do right now is take out your, of course, silenced cell phones and set a reminder. Remind yourself to look at the moon in 2 hours and 25 minutes. Why 2 hours and 25 minutes? That's how long Neil Armstrong was out of the lunar module on Apollo 11. That's about how long I spend in the car every day, regrettably. And that's a round trip, not one way. That's okay. And that was it. 2 hours, 25 minutes to do the first human reconnaissance of a planetary surface, to set up a very simple scientific package, and really set in motion, 50 years later, a revolution in not just planetary science, I'd say, or in Earth science as well. Because it was those first samples that came back to the Earth just a few days later. And that's another important thing to remember, is that Apollo 11 launched on July 16th and splashed down on July 24th. As much as Amazon is amazing, it takes me longer to get certain things delivered to my house than it did to get lunar samples delivered from the moon to the Earth. And there's the challenge for Jeff Bezos. So now, 50 years later, we have the Lunar Reconnaissance Orbiter. And I apologize for everyone. This is very dizzy. This will make you very dizzy. But this is the Apollo 11 landing site as viewed by LRO within the last 10 years. And from orbit, we can see the descent module. We can see the bottom half of the lunar module on the surface. You can see the experiments left behind. We add here a cartoon rendering of the descent stage for reference. You can see the boot prints left behind by Neil and Buzz. You can see the large crater, West Crater, that Neil Armstrong was landing towards and had to avoid in his descent. You can see the blast zone, the bright area around the descent stage, where the regolith, the surface, was kicked up. And you can see, of course, that Neil Armstrong took this ultimately unplanned excursion to this small crater. And this is a panorama of images he took at that crater, Little West Crater, which is shown at the right here. And of course, everything was planned on their EVA. Get out, do this, do this. They spent a lot of time trying to figure out and make sure they could walk around on the surface. But they also didn't plan on much of the geology. Collect samples, collect a core tube sample, set up the experiments. In flying over, he recognized that there was an impact crater there that he thought, well, that'd be a good place to go sample. And so it was only until they developed these images and realized that he had done this little excursion off to Little West Crater that they asked him, well, what was that all about? Well, I thought it would be a good sample to collect. There's a good geologist right there. And just for scale, this is the Apollo 11 traverse path on the National Mall. We're, of course, off to the side here. But you can see that in that 2.5 hours that Neil and Buzz were out on the surface, they did not go out very far. They covered the National Mall. I like to show this usually in the context of the infield of a baseball diamond. I wish that the Nats could get out of the infield of a baseball diamond these days, but that doesn't happen. But I think it really shows that this monumental event in human history took place in a condensed period of time in a very small space. And even though it was that small a time and that small space, the samples they brought back, the data they brought back, the experiments that were left on the surface, and the information that came back from that transformed our understanding of the solar system. And now, of course, Apollo 11 was just the first in a series of missions. This is a visualization of basically what the moon would have looked like in that period of time from July of 1969 to December of 1972. And Apollo 11 was just the first. It was a successful mission and followed very closely in time by the Apollo 12 mission. I can't kind of think of what it would have been like to have been around at that point in time where there were missions to the moon launching regularly. I think we all get excited about our new favorite TV series coming back, but hey, there were new missions to the moon going to, 2-3 times a year. Of course, Apollo 12 came on later on. It landed in November of 1969. And, of course, Apollo 12 had the goal of not just landing on the moon, but because Apollo 11 basically landed 3 miles long of their intended landing site, and there wasn't a great knowledge of where they had landed until the images came back, there was the desire to have a pinpoint landing, not just to demonstrate we could go to the moon, but we could call our shot. And so at the bottom right-hand corner is a bright little speck, which is the Surveyor 3 lander. And of course, if you go down the hall, and this is just mind-boggling that I can say this, you go down the hall, the camera that was brought back from that lander, which had landed on the moon 3 years before, is on display here, which is just like, whoa. Anyhow, so Apollo 12 followed hot on the heels of that, and they landed, of course, just within a short walking distance of the Surveyor 3 lander. Here's Surveyor 3. Here's a picture taken by Surveyor 3 several years before. And what's amazing about it is that the only way they could figure out where Surveyor 3 landed, there was no subsequent mission that, there was no LRO equivalent. There's where we landed, and we couldn't see the lander. But based on the images from the lander, they were able to triangulate where they thought Surveyor 3 should be. And then, of course, Pete Conrad and Al Bean Winton verified that supposition. After that, there was the Apollo 13 in-flight incident. So there was a hiatus in exploration, but early in 1971, Apollo 14 landed on the moon. This is where we get to play our favorite game, find the lunar module descent stage. And of course, right here is where the Apollo 14 descent stage is. You can see in the footprints that Alan Shepard and Ed Mitchell left behind. And they, of course, did a more extensive traverse. They tried to get to the summit of Cone Crater here. They got very close, but had to turn back beforehand. And what Apollo 14 was the last in the sort of early stages of Apollo exploration of the moon, where they didn't have a rover. They were actually carrying around sort of similar to a shopping cart of scientific experiments. It was where science became more and more a part of the mission than just sort of an add-on. After that, we sort of can take a look back on what they did. Again, here's our National Mall. Apollo 11 is, again, just a blip in the nicely new planted grass. Apollo 12 went a little bit further, but not tremendously far off the mall. And Apollo 14 had a nice traverse from right here, almost to the U.S. Capitol. And so this pre-extensive exploration of the moon really was limited by where the two astronauts could walk safely with their spacesuits. After that, we kicked into more or less high gear. Before, I talked about wanting to land in flat or relatively rock-free locations. Let's change that with our view of the Apollo 16 landing site, which landed in the rugged highlands of the moon. The Apollo 16 landing site is right between what now is we call North Ray Crater and South Ray Crater, right in the middle. Astronauts Young and Duke were able to, in their rover, drive from crater to crater, sampling materials ejected by by these impact craters, and really kind of move into a new era of lunar exploration where science was driving what they were doing. Apollo 15, which had come several months before, was the first of the so-called J missions with the rover, and what those really demonstrated were the possibilities of sending humans to do geology on other planets. And now just to sort of reinforce the point, again, early we wanted to avoid blocky craters. This is that, I'll go back one more. This is that same map I showed earlier of rock abundance. You can see that overall the area is blue, very safe, but around these two impact craters you have lots of blocks, which again, as a geologist, we wanted to go get those blocks. We wanted to know how old those craters were. We wanted to know what was exposed. And so unlike previous missions, the scientists began to win the day. They began to say, hey, let's go and explore these interesting and dynamic places. And the engineers, having the confidence of the previous missions, knew that we could do that. And then we get to what I think is the pinnacle of science and exploration, the Apollo 17 mission. December of 1972, not only the last of the Apollo missions, but and I don't want to say the last or the first geologist to walk on the moon. I want to say the most recent geologist to walk on the moon. Because I'm convinced that when we go back, eventually we'll go back with scientists, with geologists, to conduct the scientific exploration at the surface of the moon. Over the 3 days of the Apollo 17 mission, they landed in a valley deeper than the Grand Canyon, which required navigation in orbit around the moon to convince themselves that they could indeed land the lunar module in the middle of that valley and conduct the most extensive exploration of the moon to date. When they landed here in the middle of the valley, they were able to use the rover to not only traverse to the south, but indeed west and east. They were able to explore a scarp tectonic feature that erupted on or was exposed on the surface. They were able to sample material from two mountains, the South Massif and the North Massif, collecting material all along the way. Now, of course, we put a lot of effort, the royal we. A lot of effort was put into planning these missions, where to go, where to collect the samples. But when you send a geologist to the surface of the moon, you all of a sudden get into a completely new dynamic. This is the Taurus-Littrow Valley as viewed from the LRO spacecraft, the LRO camera. We slew the spacecraft off the side to get these wonderful, as I call them, out-of-the-window views of the moon. And what you see here is the valley of Taurus-Littrow, where two astronauts spent 3 days doing geology. What a great idea. When they went there, they knew, based on the images that they had in hand, that they would be able to sample material from all across this area. They could sample material kicked up by this fault, the Lee-Lincoln Scarp. They could sample that bright material coming off the South Massif, a landslide. They could do things that they thought they would, or they had hypotheses that they'd want to test when they're on the surface. We now, with LRO data, and this is a radar image, so now you're not just seeing the surface, you're seeing surface texture and properties revealed in the data from LRO. So this black and white image is radar data, and it shows not only the smooth floor with lots of impact craters, wonderful impact craters, but this rugged mountain range with all of these dark fissures. These are potentially volcanic fissures or represent fractured crust of the moon exposed at the surface. When we look in this oblique view, and this is an image that LRO, the camera on LRO took looking out the side when the sun is very high in the sky, and you indeed see color differences very, very visibly. In here is where you can see there's a few bright pixels. That's the descent stage, the bottom half of the lunar module still sitting on the surface and the region around it that was kicked up when they landed and took off. But you also see this wonderful dark feature right here. This is the target of the 4th station on their exploration of the moon. This is the so-called Shorty Crater, and incidentally, everyone should go and read where Shorty Crater's name comes from, because it's not from some history thing. There was a book in the 1960s called Trout Fishing in America. Anyone familiar with that? Which I haven't read yet, but it seems like it's one of the most pinnacle, like, hippie books. And Jack Schmidt, in reading that book, there's a character called Shorty, and so he named that crater after it. So it was not all, engineers and button-up types. There was a little bit of flexibility put in there. So they went to Shorty Crater because they wanted to understand what that dark material was. It was a young volcano that kicked out material. What was exposed there?
Okay. orange soil. Well, don't move it till I see it. It's all over. Orange. Don't move it till I see it. I've stirred it up with my feet. Hey, it is! I can see it from here. It's orange. Wait a minute, let me put my visor up. It's still orange. Sure it is. Crazy. Orange. I've got to dig a trench, Houston. Copy that. I guess we better work fast. It really is. It's the same color as these.
So, one of the most profound discoveries in the history of Apollo was first thought, well, is it cheese? What are you talking about? But I like to think that it wasn't, I mean, part of what was the benefit of having a geologist is that he recognized that something's unusual. There's orange? And you can hear in his voice, this is not the standard, I'm going to collect this sample, I'm going to put it in this bag, I'm going to do this. It was this excitement. I've just seen something amazing. And then Jack immediately starts thinking, I'm going to do a trench. He's not waiting for someone in mission control to tell him, oh, you'd better do a trench. He knows that this requires a trench. You also hear the Capcom saying, well, you better hurry up, because we got to get moving. And so one of the most profound discoveries of the Apollo program was, one, by accident, and two, done in, again, a very short period of time. And I think what I love about this clip is, first of all, it's the excitement. You can hear the excitement in both of their voices, that they've just found something surprising. They've just discovered something that 10 years ago was found to contain water in it. And those orange glass beads, which erupted from the deep interior of the moon, reveal water inside the moon. They reveal a more dynamic, different moon than we had expected and that we had known prior to 2008. And it was that discovery, because we had 2 astronauts on the surface, and we had 1 geologist on the surface who knew that that was important enough to collect and sample and bring back to Earth just a few days later and have preserved in Houston for analysis 40 and 50 years later. And that's the real benefit of Apollo and having sent humans to the moon, is that they could make these sort of fortuitous discoveries while they were there. Incidentally, this comes from a website, apollo17.org, that a friend of mine has generated, and he's working on one for Apollo 11. It will blow your mind. And to synthesize Apollos 15, 16, and 17, we see that they were able to traverse great distances with their rover. They were able to go much further than the previous 3 missions had gone. Now, with the local traffic, this would take more than 3 days, of course. They would have been able to go to Nats Park, maybe or maybe not a good idea these days. But the ability for astronauts to get further, to go further and do more on the surface really expanded their capabilities and the opportunity for discoveries. Again, on Apollo 17, Station 4 is over here in Arlington, whereas they landed here on the Mall. That ability to go to diverse locales and explore diverse locales really was one of the most profound, important things that Apollo was able to do. What next? We turn our eyes to the south pole of the moon. And there in the south pole of the moon lies an incredibly different terrain, a different area than explored in those 6 locations along the equator, those 6 Smithsonian museums along the Mall. Going to the pole of the moon can afford us the opportunity of going to that place that we all thought of going, whether it's the National Zoo, the waterfront, the Potomac, Mount Vernon, perhaps. All of these Apollo sites are limited, but we want to go someplace different. This is a view of the south pole of the moon, Shackleton Crater, which we'll all hear more about in the coming weeks, months, and years. The south pole of the moon is located roughly around here, I think. And so when we go to the south pole, and not just this location, but somewhere near the south pole, we're going to be exploring not just a different terrain, but a polar environment on an airless body. We know it has water. We know it has volatiles. There are incredible things left for us to explore. And when we go, whether we do an Apollo 11 or 12 style exploration, so this is, again, the rim of Shackleton Crater along here. And you can see that those small locations, there's great diversity in geology to explore. Small craters, material kicked out from Shackleton. And this is just an example. We don't know where we're going to go in 2024. But when we go there, thanks to what we've learned from Apollo 11, 12, 14, 15, 16, 17, we're going to go and we're going to learn so much more about our planet and our place in the solar system that I can only begin to dream of what those first professional papers coming out in the weeks, months, and year following that first exploration are going to be like. So when you go out tonight and look at the moon, don't just look and try to find your favorite. Everyone's got a favorite crater, right? Don't just try to find your favorite crater or the Apollo landing sites. Look at the 8th continent of the Earth. And the one way that we can look at the rest of the solar system and begin to unravel what we think we know about how the Earth, our solar system, and indeed any solar system in the universe has evolved through the lens of the moon. Thank you.
Thank you. Thank you. That was amazing. We have time for a couple questions. Yeah.
What's the cause of the orange color?
What's the cause of the orange color?
The orange color in those glasses, volcanic glasses, was caused by titanium in the orange glasses. We didn't know at the time. In the immediate aftermath, Jack Schmidt started speculating, oh, it's oxidization, it's water, it's rust. And only once we got the samples back in the lab could we see that it was actually due to the titanium in those glass beads. And indeed, when we went back and looked at the soils from the previous Apollo landing sites, we saw similar colored glass in all of the other soils. Apollo 15 famously collected green glass. There were no missions from Tennessee, so we didn't find any blue glass. That's a joke, I'm sorry. Can't pass up a bad pun. I'm a dad, after all. I have to have bad puns.
More questions? Yeah, there. So 18, 19, 20 got canceled. Where were they going to go, and are those potential sites to go visit?
Yeah, so 18, 19, and 20, they got canceled in 1971 or so, but there were some tentative landing sites selected. Tycho Crater had been always identified as a possible landing site, obviously way far from the equator. The Marius Hills, Alphonsus Crater, there were a number of places that were identified then that were geologically important and still remain interesting. I think Marius Hills, which represents a different type of volcanism on the moon, is potentially one of the more, well, I won't say one of the more interesting. They're all interesting. It's like one of my favorite beetle albums. Well, they're all my favorite.
Marius Hills.
Marius Hills would be a great volcanic, yes, in deference to our volcanic experts here, Marius Hills would be a great location to go. I think the only place that would be not good to go to would be land right next to Apollo 11. Like, no, we don't need to do that.
Except we wouldn't mind a few of those artifacts back into the museum.
As long as they're
they're-
properly curated along the way back.
Exactly.
Most important.
So from a geological perspective, the 2024 mission, what do you expect to see, the big science headlines?
So, if we're able to go to a place near the South Pole in 2024, get those samples back, the initial response, and we're just seeing publications now coming out from the flyby of MU-69 Ultima Thule, so that's several months later. So I would expect several months, 4 months after those first samples come back, the initial compositional assessment. Most importantly, though, volatiles. How much water is there? Other volatiles, organics. What is that environment like? I talked a lot about the geology, but the moon is bathed in solar wind. The moon is this really interesting environment where it's interacting with, and I'm a geologist, so for me it's just all stuff coming off of the sun. And so there's an interesting just environment at the moon. We don't think of the moon as having environments, but the polar environment of the moon, not only is it very, very cold, but again, has this bathed in solar wind in a very unique way. And so I think those first papers will talk about presence of volatiles, solar wind composition, and really what that environment is like. And I think NASA would be most interested in the volatiles. What's the resource potential at any of those landing sites?
We have time for like 2 more questions, right up there.
Possibility of landing in the site where mountains look
And part of that is due to the fact that at the South Pole, the sun is always coming in, essentially like the sunrise and sunset, so all topography is enhanced. It's also the rugged highlands of the moon, so it's been completely battered by impact craters. And so I think those first images that would come back from a polar landing site, whether it's where I showed or somewhere else, are going to, well, when a human clicks a picture, whether it's a picture from the ISS, there's something spectacular about that. Now, nothing's going to look quite as sharp as the Alps because the moon's surface is constantly being eroded by micrometeorites, but I think those first pictures, and again, they'll come back in high-def color right away because that's how we live in right now. We're going to, black and white TV ain't going to cut it anymore. And so I think those first pictures, because humans are taking it, are going to be spectacular. If you've seen the pictures coming back from the rover on the far side of the moon, they're stunning because it's the far side of the moon. As a classic rock fan, I hesitate to call it the dark side of the moon, but I think the Pink Floyd folks are really glommed onto something important there. They'll still be majestic, but again, you're going to have the sun very low on the horizon, so it's going to be quite a challenging illumination environment to go to.
There was a hand right over there.
For the difference between the human missions and the robotic missions, are you already planning out, like, are there places that you'd like to go with humans but you'd be satisfied with robots? And have you been trying to argue for some more rugged terrain that you wouldn't want to send people, but you'd be happy using a laser if it was
So the difference between human and robotic landing sites, and are there more rugged landing sites that we'd risk a robotic mission?
Yeah, that's a hard question. There are places that I would love to send a lander to the far side of the moon and bring samples back tomorrow if I could. I know that I can't do that with humans. I mean, I can't send a rover or a lander to the moon tomorrow. It takes more years than that. But shorter time than the plan to send humans. One of the things that we've learned from the LRO data that we have now is that engineers will always be conservative. But we can go to that, when we talk about the rugged highlands, it's not landing on, there are smoother places in the highlands. Apollo 16 showed that we could go to the highlands. So I don't think there are places that I would want one or the other. I think it's a question of time. Now, a rover or a robotic lander that could go grab a sample and come back, that you don't necessarily need to have a human do that. We know there are geologically interesting places that just getting a kilogram of the regolith, that surface material, would be adequate for what we think we need. But as we showed with the last 3 Apollo missions, when you have humans that have capabilities of moving, even on Apollo 12 where they could walk greater distances, astronauts on the surface can do amazing things. And so if we can go to really dynamic, interesting environment, every place on the moon is interesting, geologically diverse locations, and get 4 or 5 different types of material in one spot over the course of 2 days, those are great places for astronauts to go. But that's a hard toss-up, but I think there are some places that are just best suited for going, getting a sample, coming back, and robots can do that potentially faster than humans can. And the Russians showed that with their 3 robotic sample return missions in the 1970s. So that's something that we've, as a population of the world, have shown that we can do.
I know there are a lot more hands, but Noah's going to be down at the base of the escalators after you exit through the back and come down the escalators. Noah will be there for not infinite amount of time, but he will be there for a bit down by the Welcome Center to answer more questions. I know there are a lot of hands. I also want to put in a huge plug. There's a generally clear sky, so our telescope is open. Our Phoebe Waterman-Haas Observatory is open for stargazing and other astronomical observations. So please go down to the far end of the museum and take a look in the telescope and see what you can see tonight. I really want to thank you all for joining us. Another thank you to Aerojet Rocketdyne and ULA for sponsoring tonight. We have one more lecture left in the series. That'll be NASA Chief Scientist Jim Green on June 19th, and we hope to see you all there. And so thank you again. Exit through the back, and staff will help point you towards the observatory. Thank you.